so this is the part 2 of the introductory course on string theory. And so I'd like to start with Calabi-Yau manifold. I really like this chalk and blackboard. It seems to work very nicely. I don't know why mathematicians don't use this type of blackboard. Anyway, so string theory is defined as we defined it in the last quarter in 10 dimensions. We'll see that in certain situations it can be more properly interpreted as in 11 dimensions, but perturbative string theory, heterotic string, and type 2 are defined in 10 dimensions. But we don't live in 10 dimensions, so we would like to compactify part of the 6th dimension to some compact manifold, and then make this sufficiently small, so for our current experiment we can only have access to 4 flat directions. So the question is what kind of condition we should impose on these 6 dimensions. And so we'll see that the Calabi-Yau provide you a very good class of a compact manifold where this is a consistent background configuration of string theory. And but I should point out that in the strict mathematical sense, the Calabi-Yau manifold is an approximation. To string equation motion, and I would like to tell you precisely in what sense this is approximation. And then still say that for many practical calculation, this gives you a very good basis to do the calculation. Okay? In certain situations, this approximate method gives you exact answer. Okay, so I'll discuss this 3 aspects of this. First is from the point of view of low energy theory. Where we approximate superstring by supergravity. So string theory contains all these excitations, so there are infinitely many particles. And supergravity consists of a metric, some number of gravity-Schwinger field. So I goes from 1 to the number of supersymmetry, and then plus other fields like dilaton and unsymmetric tensor field. But these are finite number of particles, and these are all massless. Okay, and so this is an approximation which is valid when the size of Calabi-Yau is larger than the typical scale of superstring. So when we define the string theory, we have introduced a notion of string tension, which gives you the mass scale and energy scale and length scale of string theory. And so if that is, so a Calabi-Yau manifold is parametrically larger than that, then you can well approximate string theory by supergravity, and you can use supergravity equation motion to determine what kind of conditions that this internal manifold has to satisfy. And there we actually pay attention to supersymmetry. Okay, so these are supersymmetric theory. So if you have a symptotic flat direction, the supersymmetry is a gauge symmetry, so it doesn't act on Hilbert space. But towards the boundary of, towards the infinity of flat space, there is a large gauge transformation which acts non-trivially on the physical Hilbert space. So there is the action of supersymmetry on the Hilbert space of supergravity theory. And so we can ask whether certain configurations are supersymmetric or not. Okay, this condition for supersymmetry is very useful to give precise condition for solution to equation of motion. Because if you have supersymmetric theory, then the Hamiltonian or energy of the theory is the square of some Hermitian operator supercharge. So this is bounded from below because Q is a Hermitian operator. And in particular, the state which is annihilated by this supersymmetry, if you have a state which preserves some supersymmetry, then it's automatically the lowest energy state possible within that class. So that is a stable solution. Okay, so if you have a supersymmetric configuration, then you're guaranteed to be stable. The reason that this is useful is at least this gives you a basis. If you start with supersymmetric solution, this gives you a basis of understanding class of solutions. If you don't, you can still solve more general solution to supergravity. But if you start with solution which breaks supersymmetry, then you might worry that there are all sorts of corrections that you are ignoring, which may become important. For example, here I have already been making approximation of solving superstring equation motion, approximating it by supergravity equation. So that's an approximation. We are also going to, for now, just solve the classical equation motion. And there are quantum corrections. So for example, if you have, so for example, the type of supergravity we are going to consider for the next few lectures have zero cosmological constant. So the flat space is, for example, solution to equation motion. However, if you start with configuration of metric and other things that breaks supersymmetry, typically if you consider one loop quantum correction, it generates cosmological constant, the dark energy. So if that happens, then you have to correct the equation of motion by one loop. That original solution is no more solution to the equation of motion. So a priori, if you start with a generic solution, it's not clear whether this process will converge and give rise to a stable solution in the end. If you start with the supersymmetric configuration, then you have more confidence that even though you are solving approximate equation, your solution can have completion in the more precise version of the theory. And so this is a good basis to start. Of course, our world is not supersymmetric, so this is not exactly what we want to consider. So we need to later find a way to break supersymmetry, etc. But we will discuss that later. But this is in terms of low energy theory. And we would like to, we are doing string theory, so we would like to understand what kind of correction that string theory gives rise to, or whether there is a more genuine formulation of this type of question in the full string theory. And so then after going through this low energy discussion, we will be discussing the worldsheet perspective. So from this perspective, we need to discuss what we mean by equation of motion to string theory. How do you formulate? How do we talk about stringy equation of motion? Yeah, this sounds like a very daunting task because string theory is essentially a collection of infinitely many different types of particles. So you have a massless sector, which is supergravity, super Young Mills, etc. And then there are massive particles, which contains, and then there is an infinite tau. So in principle, you can have infinitely many type of particle and infinitely many equation motion to solve. So that's how do you track that? So it turns out that there is a nice correspondence between the classical equation of motion of the full string theory, not the approximation, to the vanishing of beta function for renormalization group. equation. So this is the equation in the sense of Ken Wilson, Gelman, etc. That you think of this worldsheet of strings of propagating space-time, and it sweep out two-dimensional surface. And you consider conformal field theory on this surface. And as we saw in the last quarter, conformal invariance on this worldsheet is important. Now, if you consider a string propagating in generic metric, gauge field configuration, etc., then the effective description of string in that background is not necessarily supersymmetric, conformally invariant on the worldsheet. So if you try to describe this in terms of two-dimensional worldsheet, the conformal invariance is broken. The requiring that you only consider configuration which guarantees conformal invariance on the worldsheet is the same as vanishing of the beta function. I will explain what I mean by this. And it turns out that this is actually fully equivalent to the classical equation of motion. So therefore, we can recast this difficult program of dealing with infinitely many equations for infinitely many types of particles into rather well-defined equation in the standard terminology of two-dimensional quantum field theory that we are looking at conformal fixed point of two-dimensional theory. I'm going to explain this terminology as we go of 2D quantum field theory. So, roughly speaking, you consider space of quantum field theory, space of all quantum field theory. So you have a space of all quantum field theory. And then there is some submanifold, which are conformal. Okay, so that kind of image. Oh, these are all infinite dimensional. Well, this can be finite dimensional or isolated, but there's in the space of infinite dimensional space of quantum field theory. And then there are some subspaces, and that's where the conformal field theory resides. And this mirrors to this side of the picture, where you can consider all sorts of background geometry where string can propagate. You can have variety of metrics, gauge field configuration, dilatons, but there is a subspace in this infinite dimensional space which solves the equation of motion. So the idea is that there is a correspondence between them. The third is application. And there are many, but I'd like to first start with the heterotic string. Compactification. This is the first very interesting construction where you start with 10-dimensional space and compactify it on Calabi-Yau manifold times R4. And so in heterotic string, you have minimum number of supersymmetry in 10 dimensions. And in the R4, what it gives rise to in this construction is that you have n equal 1 SUSY theory, which look like standard model minimum supersymmetric extension of standard model like theory, with a generation of quarks and leptons and gauge fields that mediate possibility of embedding SU3 cross SU2 cross U1 gauge symmetries with Higgs mechanism to break the gauge symmetry, etc. So this gives rise to the low energy theory, which contains essentially all the desired feature if you consider supersymmetric extension of the standard model of particle physics. So this was actually sort of one of the interesting, important construction of string theory to go approximately to look like our real world. And so this is an interesting example I'd like to discuss. There are many other things that I would like to discuss: understanding Zeiberg-Witten solutions, strong coupled dynamics of supersymmetric series, etc. So there are many, many different things we can discuss. But depends on the amount of time we have, so we'll see. Okay, so that's the plan for the next few weeks. I would like to also get to D-branes and also black hole information paradox, but that may be overly ambitious, so we'll see how it goes. Okay, so but you can also ask me if you want to know. So there was already some students who sent me some email asking me, well, I'd like you to cover this or that. So you can send me a request. I cannot guarantee that I can fulfill that request, but I'll try. Okay, so any questions so far? Okay, so today what I'd like to do is to discuss the following question: that suppose you consider 10-dimensional space and compactify part of the space to 6 dimension, giving rise to 4 dimension, and request that this configuration preserve some supersymmetry. What kind of condition does this have to satisfy? And how do you construct such geometry? And how do you study this? So I'd like to discuss those things. Okay. So what are the conditions? So you start with 10-dimensional space, compactify on 6 dimension times R4. So you can ask what kind of condition for supersymmetry. Okay? So there is actually a very good way to identify the condition for supersymmetry, which is to see how various background field transforms under supersymmetry. Okay, so supersymmetry tells you that the metric transforms under supersymmetry. So there is a supersymmetry transformation epsilon, and the metric transforms into derivative of Rarita-Schwinger field. So epsilon of delta mu, delta bar psi mu, etc. Nu, and then symmetrized, etc. So typically what happens is that supersymmetry transforms the bosons into fermion, and then transforms fermions into boson. Okay, and and then epsilon is a spinor. And if the configuration is supersymmetric, that means that there is certain spinor field for which the right-hand side vanishes. So that is the condition, right? And so what does it mean it vanishes classically? Well, classically it means that if you consider vacuum the configurations that you are interested in and evaluate the right-hand side, that should vanish. Okay, so the condition is equivalent to, say, the classical SUSY. Classical supersymmetry means that the right-hand side is equal to 0 for the configuration. That is a condition. Okay? Now, it's basically the expectation value. Quantum mechanically, what it means is the expectation value of this. Now, fermions have no expectation value because expectation value is a real number. Fermions anti-commute with each other. There is no way to assign the expectation value of fermion by real number which anti-commute with each other. So fermion, the right-hand side of variation of the bosonic field are always 0. So the only non-trivial condition that you need to satisfy is this one. Okay, so this is the condition. So therefore, the vanishing of epsilon times boson. So the condition is that there is some spinor field for which epsilon vanishes. So that's the kind of condition that we should be after. And so that means that we only have to worry about the variation of fermions. And in supergravity, the fermions that we should consider as spin 3 half-field, because these are superpartner of the graviton, right? So therefore, we should consider Rarita-Schwinger field or a graviton, which has a spinor index and then the vector index. Right, so it's a spin 3 half field. So spin 1 from vector and spin half for the spinor. And the supersymmetry transformation is typically that if you transform this spinor field, it becomes del mu of epsilon alpha, where epsilon is a spinor field. And it's a supergravity, so that means that it's a gauge symmetry of supersymmetry. So therefore, supersymmetric parameter, it becomes position dependent, so you can have covariant derivative. The covariant derivative with respect to the spin connection of the metric. So this contains information about the geometry of the target space, right? So this is a condition that therefore supersymmetry requires. So let me write it explicitly. So therefore, supersymmetry requires that there is some spinor field such that the covariant derivative of which epsilon vanishes. Namely, existence of covariantly constant spinor implies supersymmetry and vice versa in this particular case. Now, this is a case for supergravity with zero cosmological constant. If you have supergravity with negative cosmological constant, then there are some additional terms, and that becomes important when we discuss ADS-UFT correspondence. But here I'm considering supergravity theory for asymptotically flat space with zero cosmological constant in 10 dimensions, which is what appears in the low energy approximation to type 2 or heterotic string theory. So this is the equation we should be solving. Now, for now, let's consider type 2 string theory to be specific. Okay, so we'll discuss heterotic string, but Calabi-Yau is solution to both of these situations. It's easier to discuss type 2A and type 2B, because in heterotic strings you have more field and you have more conditions that need to be satisfied. So let's focus on this particular case first. Okay, so in this case, this is the only equation that one should solve. Okay. There are also other fermions in addition to Rarita-Schwinger field in general. For example, in the case of a heterotic string, there are also a super partner of the gauge field. Heterotic string has SO3 or SO32 or E8 cross E8 gauge symmetry, so there is a super partner, the gauge nodes. And so you have additional conditions that has to be you have to satisfy. Okay. But let's first consider this case, and we'll discuss variation of that in the context of a heterotic string later. Okay. So the question is, what is the condition? Okay. So we would like to solve this equation for supersymmetry. Okay. So let's think about what kind of conditions that give us. So let's specifically consider a 6-dimensional space. Okay, and delta is the covariant derivative of spinor, and as I said, so that it's a covariant derivative, so it knows about spin connection in the spin field, spin bundles, called the spin connection. And so therefore that contains a geometric information about the L6. And so in the 6-dimensional space, the connection is for SO6 bundle, right? Because it's a 6 dimension, so you have a tangent space at each point in 6 dimension. the tangent space can rotate by SO6 rotation because it's a 6-dimensional space. And so as you go from, so you have M6, and at each point you have a tangent space. And then at another point you have a tangent space. And then as you move from one point to another, you have to parallel transport. And that gives rise to connection. Well, this gives you connection for the tangent vector field. But it implies connection for spinor field also. So for covariant derivative, so for the vector field, it gives rise to SO6. But SO6 is SU4 as a Lie algebra. And connection is about Lie algebra, so you can think of this as the same thing. So this 4 has to do with, or as a Lie group. So these are these have the same Lie group. And this 4 has to do with a number of components of spinor. So you know the formula that the number of components of spinor is equal to 2 to the d over 2, and I think it's this way. I think. So for d equal 2, d equal 6, this gives rise to 8, right? So this is 8 for d equal 6 because it's 2 to the 3. And so what this 6 means that you have actually 4 wire spinor with one chirality and 4 wire spinor for the other chirality. So this 8 is decomposed into 4 plus 4 bar, where these are wire spinors of opposite chirality, and this is actually the fundamental representation of SU4. So that 4 is related to the fact that the wire spinor in 6 dimensions has 4 components. Okay. So that's SU4. So you can think of this connection of this. So you have M6, the Calabi-Yau space, which is going to become Calabi-Yau space, and on this space you have a connection, and then spinor field is changing by this SO4. This equation means that there is actually a spinor field. You can identify spinor field which do not change as you move around. Which do not change as you move around. For example, this is covariant derivative is 0. What it means is that you can actually so you pick a point. You pick a point anywhere on M6. This particular spinor is covariantly flat. So that means that you can actually parallel transport this spinor to anywhere. And you can essentially think of this as a constant spinor field. Right? So with respect to this connection, there is actually a constant spinor field. It doesn't change. So usually if you move spinor around in the space, it moves around by SO4 rotation. But the fact that there is a covariantly constant spinor means that there is actually direction in 4-dimensional direction which don't move. So the actual connection acts on the transverse direction. So that means that the connection, so this means the existence, so the fact that you have some spinor field such that the connection is spinor field is covariantly constant means that the connection is in SU3, inside of SU4. Because there is one direction in 4-dimensional space which doesn't move. So all the action of the connection has to be transverse direction, and that's 3 out of 4 direction because 1 is taken. So that's SO4. Mathematically, this you can think of as the little group. There is a notion called little group of, in this case, SO4. And the little group is the following thing that you pick some particular vector in the representation, and you require that vector doesn't move. And so suppose you have some group acting on some vector space, and you require that one vector don't move. And then you ask what is the remaining subgroup of the group which preserves this vector. And that's called little group. So the little group of this covariantly constant spinor is SU3. So what it means is that even though generically, if you consider 6-dimensional space, the connection is SU4, takes value in SU4, actually, in order to have covariantly constant spinor, the connection has to be restricted to be in some SU3 subgroup of SU4. That is a condition. So that's the condition for supersymmetry. Conversely, if the connection can be restricted to SU3, then you can always find one spinor which preserves this. And so therefore, this is necessary and sufficient. So you see that if you have one and only one covariantly constant spinor, then the connection should span over SU3 subgroup of SU4. Conversely, the connection of the manifold goes around SU3 of SU4 and leaves one spinor but not more. Then there is one covariantly constant spinor which satisfies this. So this is necessarily sufficient. So this kind of subgroup for which connection effectively acts is called holonomy. So, for example, if you have the connection itself is not gauge invariant concept. The gauge invariant concept is a curvature. And so if you go around the manifold parallel transporting some vector or spinor, come back to the same point, then you can compare what kind of actions that the connection has on that particular vector and compare them in a gauge invariant way because you are comparing two vectors or two spinors at the same point. And then in general, what happens is that if you have a manifold M6, for example, and if you start some point, and then you have some vector, and then you parallel transport that vector along some path, and come back to the same point. It's going to move in. It's going to generally be in different direction, and you can ask how much they are different, and that difference is a curvature. So the curvature typically takes, so the curvature takes value in the holonomy of this manifold. The holonomy is more general notion. Sometimes, for example, the manifold may have some kind of non-trivial topologies, and then you can have a situation where you can go around that cycle and come back, and then the direction of vector might have changed also if you do that, and that's also holonomy, right? So holonomy is defined by sort of set of the following things that you pick any point in the manifold and you consider all possible closed paths on the manifold and the parallel transport the vector or spinor or whatever the vector bundle, the element of the vector bundle you're considering. You move that around and come back to the same point and ask how much it is. And then you can say, if you think of all possible closed paths on the manifold, you can easily see that it makes a group. Because you can multiply, right? Because if you have a point, if you have a closed path, it gives you, so for each closed path, it gives you an element of the group. Yeah, so let me do it more precisely. So maybe it's useful to define what I mean by holonomy group. Okay, so holonomy group is a following concept. Suppose you have a G bundle over some manifold M. Okay, and then I'm going to define the holonomy for this G bundle. So here we are considering SU4 bundle. If you have tangent space for n-dimensional space, you have SON bundle, right? So in general, you can consider some G bundle where G is a Lie group. Well, you can also consider some finite group, but let's try not to generalize this too much. So let's consider some Lie group and consider G bundle. Okay? So then what I'm going to do is start from any point on this manifold and then consider closed path. Okay, and then parallel transport that so you have a vector bundle where with G action, and you can ask how the vector transforms and along the closed path. So this gives you a map from gamma to G of gamma to the group, right? Now it's clear that this contains identity, because you can take gamma to be as small as possible, and in the limit when the gamma shrinks to a point. So if the gamma is trivial, then G of gamma is an identity. So G contains identity, right? Now we can also multiply, because you can have two passes, gamma 1 and gamma 2. And then if you can combine them, you can go around gamma 1 and then come back. Because in this definition, I didn't say that you cannot come back to the same point in the middle. So you can go around gamma 1, come back to the same point, and gamma 2, and come back to the same point. So that means that you can actually compose gamma 1 and gamma 2, and then it's a product. Actually, its product acts in the opposite order, but it doesn't matter. So you can actually define product. You can have inverse. You can have inverse because you can start going around one direction, which I call gamma, and you can actually backtrack, come back to the same point by inverse, and that gives you trivial transformation because you parallel transport in one direction, one way, and you just rewind it. So therefore, G of gamma multiplied by G of gamma inverse is an identity. Okay, so it satisfies all the group properties, satisfies associativity too. So that means that if you consider this, and you can consider all the images of this map, so namely that the holonomy group is G of gamma for all the paths starting and ending at point P. So then you can define some subgroup of the group associated to each point on the manifold. Now, this definition of subgroup depends on the point. But you can show that it's actually the structure of the group is independent. Structure of the subgroup is independent of the choice of the point. Because for example, suppose you have another point, Q. So for this point, you can define HP, and for this point, you can define HQ, right? These are actually related to each other because you can have a path from P to Q. If you cannot find such a path, then they are different manifolds, so we don't have to worry about it. And if the manifold is path connected, then one should be able to find such a path. And then you can show that actually this is actually related to some conjugation, where G is basically the parallel transport from P to Q. So if you have two subgroups related to two different points on the same manifold, then the holonomy group for P and holonomy group for Q are conjugate to each other. So therefore, even though they are not strictly the same group, same subgroup, but their group structures are identical. Okay, so therefore, essentially for given manifold, there is actually unique subgroup, or at least the structure of the subgroup, modular conjugation. So that's what's called the holonomy group. Okay, so that's the definition of the holonomy group. So what I wanted to say was that the existence of covariantly constant spinor is equivalent to say that the holonomy group is SU3 inside of SU4. Okay, in the case of M6. Okay, you can ask what the general situation is. Okay, so let me clarify this a little bit more. So what this means is that in this case, epsilon takes value in 4 plus 4, as I said. These are fundamental representation of 4, SU4. And then this is also fundamental representations of SU4 with opposite chirality, which I denote SU4 plus and SU4 minus. Okay, now, so what this means is that you can actually decompose that with respect to the SU3 representation. So namely, it is 1 plus 3 plus 3 bar plus 1. Right? So this is a triplet of SU3. This is a fundamental representation of SU3. This is a conjugate. This is the opposite chirality, and then there are singlets. So this is actually epsilon, and this is actually the conjugate of epsilon, the opposite chirality. So what it means is that it's actually gamma 7 acting on the epsilon. So you can take linear combination of these to project onto some particular chirality when necessary. So where gamma 7 is a product of gamma 1, gamma 2, gamma 6, because we are considering 6-dimensional space. Okay, so this is great. So that means that now we can understand what is the geometric configuration for existence of supersymmetry. Then the holonomy, if you have a 6-dimensional manifold, if you want to compactify it, the manifold has to be compact with finite volume. But if you can find manifold whose holonomy is SU3 inside of SU4, then that is necessary and sufficient for preservation of supersymmetry, at least for type 2 supergravity in 10 dimensions. Okay? Later, actually, it's going to become useful to think more general situation. What are the possible holonomy of the manifold? And in fact, interestingly, this is completely classified. What kind of holonomy that manifold can have? And so there's work by Marcel Berger. So there's a thing called Berger's list, which classify holonomy group. So basically, the classification is basically subgroup of SOD. What kind of subgroup of SOD you can actually realize? And so that is where it's actually satisfied actually 2 conditions. First is that we are considering M to be simply connected. And irreducible. So you can have, for example, product manifold, and they may have different holonomies. So you just pay attention to simply connected component, and we don't consider symmetric space. Such as G over H, because then if you consider that, you can consider all sorts of G's and H's. And we consider non-supersymmetric cases. And so let me discuss classification for later convenience. Okay, so here is the Berger's list. And when listing this, I would like to also list the number of covariantly constant spinors. With a plus or minus chirality. The choice of plus and minus chirality depends on the convention, but whether if you have several spinors, covariantly constant spinors, whether they have the same chirality or opposite chirality is an invariant question. So we can discuss those things. Marcel didn't consider the notion of a number of spinors, covariantly constant spinor, but it's useful for us to consider. And it can be easily read off from Berger's list. So let's study that. So consider d-dimensional Riemannian manifold. And we consider only the connection that is induced by the connection, the Riemannian connection, the Christoffel connection. Okay? And then you can infer the spin connection from the Christoffel connection. So most general situation is SOD connection, because that's the generic configuration of the Christoffel connection. And for generic, so we suppose you consider holonomy, and holonomy just exactly this equal to SO4. So that means that it moves around spinor in all possible directions. So there is no covariantly constant spinor which is fixed under this connection. So clearly, in this case, plus there are no covariantly constant spinor. So the next is UN holonomy, and that happens only when the manifold has even dimension. So UN means that you basically pair up. So suppose if it is even, so you have even dimensional manifold, you may consider combining a pair of real coordinate into complex coordinate. And you can think of that as complex coordinate. Now, not all the manifold, for the manifold you can do that. The manifold has to satisfy certain condition in order for the complex structure to be introduced. And then there is a question of whether the metric is compatible with the choice of complex structure, by which I mean the following. So suppose you have this coordinate mu, which goes from 1 to d. And if d is even, you may consider combining them into complex coordinate, right? So d is 2n, okay? And but in the case of UN holonomy, the metric with respect to this complex coordinate has a particular property. The first is that you can consistently choose this complex coordinate, which means that if you have, say, coordinate patch between the two coordinates z prime and z, then the coordinate transformation between z and z prime is holomorphic. Well, let me write it as w. So w, suppose you have coordinate patch with w, and suppose you have coordinate patch with z. Then, in order for this complex coordinate to be useful, it's better be that coordinate transformation is holomorphic. And you cannot always do that. If you have a general real coordinate, you cannot find zi holomorphic coordinate so that you can recast the coordinate transformation in this way. And so that's actually a condition for the complex manifold to exist. And another condition is that this complex coordinate fits nicely with the metric. So what it means is that the only non-trivial component is a mixed component of z and z bar. you have only mixed component of zi and zj bar. And for example, gij or gi bar, j bar has to be equal to 0. And moreover, so this will be actually minimally required, but the holonomy become un only when there is actually some scalar function, so that the metric can be written as derivative of this k. And this k is called scalar potential. Okay, this is a very important concept in the following. So we can discuss it. By the way, I will be using quite a bit of these complex geometries, and later I will be using some notation of the differential forms, etc. Unfortunately, I don't have time to cover all this. Fortunately, I have given separate Caltech course on this. There is a YouTube also, and I can also share my lecture note on the Canvas site. So I can link those on the Canvas site. There is a YouTube video of the entire course that you can see on my YouTube channel. So I can give you the link to that. So there is actually a special there is a lecture. There is a day where I discuss differential forms. There is a day when I discuss scalar manifold, etc. So you can look at those things. Okay, so you can be the supplemental material. If you're not familiar with this, I recommend you to take a look at that. Okay, so this is a scalar manifold. Okay, so scalar manifold is a complex manifold for which the metric is expressed in terms of the scalar potential. Okay, this is not yet supersymmetric. So in general, if you have a generic SUN holonomy manifold, there is no supersymmetry. And the reason is that there is the reason is that spinor get mixed up by this U1 part of SUN. Okay, so finally, there is a situation where you can have supersymmetry. And so that is the case when the holonomy in the Berger's list, holonomy is SUN, which is a part of UN. And the difference is the U1 part is vanishing. And this is what's called Calabi-Yau manifold. Okay, and so in this case, you have actually two covariantly constant spinors, and they have opposite chirality when n is odd, and the same chirality when n is even. So, for example, in the Calabi-Yau threefold, six-dimensional Calabi-Yau manifold, n is 3, so it's odd. So we have seen that you get a spinor of opposite chirality. But for example, when you consider 8-dimensional Calabi-Yau manifold, or n equals 4, then you get actually 2-0 supersymmetry. So so this even and odd mean that basically there are two solutions. So namely, if you have a solution to this equation, then gamma d plus 1 epsilon is also a solution. So it's basically the question of whether this and this has the same chirality or opposite chirality. Okay, and then that depends on whether n is even. Okay, and okay, so what is actually, so the holonomy is something that sounds like global property, right? So you do a parallel transport of spinors or vectors and come back to the same point, and what is a group acting on it. But actually, you can write some local equation, and in fact, you can write down differential equations which constrain the metric. And so it's actually a nice equation. So let me write it down. So what is the condition we should look after? Well, so I said first of all you start with SO2D, and then you consider subgroup UN. So what is the subgroup UN? Well, so in SO2D you have a vector, you have a coordinate, and infinitesimal variation of coordinate gives you a basis for cotangent vector, and then it's rotate, right? It's rotate, and it's rotated by SO2D. Now you consider a complex manifold. You have a complex coordinate. You consider infinitesimal variation of the coordinate. It gives you a tangent vector. And tangent vector in the case of SU and holonomy is organized into holomorphic one and anti-holomorphic. Now, so we want to consider some further subgroup of SUN. So that means that U1 part is acting trivially. What does that mean? Well, the way that complex coordinates get transformed into each other is characterized by Riemannian metric. The Riemann curvature, Rij bar KL. So if you go around the parallelogram in the space in the direction of I and J, then it's rotate the holomorphic tangent vector in the component of KL. That's what this Riemann curvature tells you, right? Now, so that means that if you restrict, there is a U1 part that don't rotate, means actually that if you take trace of this, then it should vanish because it should act trivially. Namely, that U1 part of UN holonomy should act trivially. And this condition is equivalent to say that rich curvature vanishes. So infinitesimal version of SUN holonomy is equivalent to the condition that rich curvature vanishes. And there's a beautiful fact. There's a really beautiful fact about the Taylor manifold, which is that the rich curvature is a very simple expression that you can actually write down del I, del J bar of log of determinant of the metric. If you consider log of determinant of the metric, and if you consider del bar of this, then it actually gives you rich curvature. You can actually check that very easily by hand or mathematically. That you plug in the form of Christoffel connection, calculate Riemann curvature, put this condition, the metric is of this form, and you can show the rich curvature takes this form. So the derivative works around that way. And so you want del bar of G to be equal to 0. Now, you see that there is actually general solution to this equation. If you have a function for which if you take derivative, so what is the condition? Well, if you have this equation, suppose you have a function for which del bar is equal to 0, what does it mean? Well, first of all, you consider this. What this means is that holomorphic derivative of del bar of f vanishes, which means that del bar of f must be some anti-holomorphic function. Right. So then you just have to integrate this. So that means that f is anti-holomorphic integral of G. But then there is an integration constant. Integration constant can be holomorphic because if you have holomorphic thing added to it, it satisfies the same equation. So that means that there is a possibility of adding something else. But the integral of anti-holomorphic thing is that anti-holomorphic function. So that means that general solution to this equation, is just sum of holomorphic function and anti-holomorphic function. Right? So this means that del I del j bar of log of determinant of g is equal to 0 implies that log of determinant of g is equal to some holomorphic function and some anti-holomorphic function. Okay, but this left-hand side, so you see that because if you have the del del bar on it, it vanishes, right? But I just show that this is the most general solution. But since the left-hand side is a log, so it's actually useful to write f as log of something. So I'm going to write this as log of omega z plus log of omega bar z bar. So namely that it's a product of omega z omega bar z bar, right? So this is a general solution to this condition. Okay, so what did I do? Well, I showed that if manifold is scalar and if it satisfies the rich flatness condition, then since Rij bar is equal to del I del j bar of log of determinant of g. So determinant of g, excuse me, the small g, determinant of g is equal to omega z, omega bar z bar for some omega. Now, what kind of omega can we have? Well, the metric, the scalar means that metric is given by this, and the metric only has ij component. Determinant is a determinant of this epsilon. Determinant means that this is actually an unsymmetric combination of gi1 j1 bar gi2 j2 bar gin jn bar, right? This is what we mean by determinant. Maybe I should divide it by n factorial. This is the definition of determinant. But if you look at it, what it means is that you consider some product of the metric, consider this as n times n bar tensor and unsymmetric. So this means that by comparing both hand sides and then request that it transforms nicely under the coordinate transformation, in order to write this equation in the coordinate invariant matter, invariant under the holomorphic coordinate transformation, then it requires that omega to be unsymmetric tensor. Or in the language of differential form, this is holomorphic n form. This is n form. Or more precisely in the language of complex manifold is n0 form. Because you have n totally unsymmetric indices in the holomorphic component and no anti-holomorphic component, so you call that as n0 form. So I'm using the language of differential form. In the notation of differential form, we can also write this as omega I1 in dz I1 wedge dz in. Okay, so this is omega. And the condition that this is satisfying is that it is holomorphic. Namely that if I take del bar of this, it vanishes. So you can have d of omega is equal to 0. So you see that vanishing of rich curvature is equivalent to existence of holomorphic N0 form. Implies existence of holomorphic N0 form. Okay? So the condition is that omega is holomorphic N0 form. It also requires that it's nowhere vanishing. Because the metric should not be non-degenerate, the determinant should not vanish. So that means that on this manifold, omega is non-zero everywhere. You cannot have 0 in this holomorphic case. So that's another condition. Okay, so these are the conditions. So we have shown that if the manifold has SU n holonomy, if manifold is n complex dimensional manifold, if it has n SU n holonomy, then it implies that the manifold should have nowhere vanishing holomorphic n form. It was conjectured by Eugene Calabi that this is actually sufficient. That if you have holomorphic N0 form, then you can also find, always find the metric which satisfies, Kela metric which satisfies the condition. And this was actually proven by Yau. So there is a Yau's theorem. Which states that if there is a holomorphic N0 form, and if it is nowhere vanishing, then one can solve this equation. Okay, so this is essentially analysis question. Well, it's geometric analysis, but it's an analysis question, namely to prove so this, you can think of this as a nonlinear partial differential equation. So the proof is that integrability of this nonlinear differential equation is guaranteed by existence of nowhere vanishing omega. So that's the heart of the proof. And if you can solve this, then it just means that if you write this as a metric, then the rich curvature is 0. So this is all what we already saw. So the important part is this, that it implies that you can actually find the Kela potential which does this. And moreover, such Gij bar is uniquely determined. For a given complex structure. And a Kela class. Kela class is the following concept, that if you have a Kela metric, you can define the differential form, which is Gij bar, dzi, dzj bar. And it satisfies the condition that it's closed, dk is equal to 0. It's a derivative operation on the differential form that is explained in my lecture on 229 YouTube video in the section of differential form. So I recommend you to look at that. So if you consider a space of solution to this equation, and it gives you a certain cohomology, and within that cohomology, the element of that cohomology determines the Kähler class. So what Yau showed was that not only you can solve this equation, but in fact, if you fix a complex structure and Kähler class of this Kähler form, then actually solution is unique. So therefore, so for given manifolds, the space of rich flat Kähler manifold is completely determined by the complex structure and Kähler class, and so that's Yau's theorem. And so that's wonderful, because then essentially we understand what is the space of solutions. So it's a bonus, right? So if you not only know that you can actually solve the supersymmetry condition, but you actually know the space of all possible solutions. So that's unusual for you see, this is a vacuum Einstein equation, right? Yeah, because Rij is 0 also, and holomorphic and that. So this is actually entirety of vacuum Einstein equation. So you are solving vacuum Einstein equation in a non-trivial manifold, and then you can, Yau's theorem says that for this class of non-trivial manifold, you can essentially classify all solutions. So it's a beautiful result. And so justifiably, the class of manifolds that satisfies this condition is called Calabi-Yau manifold. Actually, this terminology appears first in the superstring literature. So after 1948 superstring revolution, there was a paper by Candelas, Horowitz, Strominger, and Witten, who showed that you start with 10-dimensional heterotic string and compactify the theory on Calabi-Yau manifold. It can give rise to low energy N=1 supersymmetry theory, which contains quarks and leptons and the gauge group SU3 cross SU2 times U1, etc. And it is in that paper that the term Calabi-Yau first appears. Okay, so that the Berger's classification continues. So let me actually say a little bit more about Berger's classification, just to complete the picture. So I told you that there is a SOD and no supersymmetry UN when D is 2N. This is a Kähler manifold, but no supersymmetry. And SUN D is 2N, and this is Calabi-Yau. And there you have two possibilities when n is even, n is odd. And then 2, 0 for n even. Okay, so there are a few more cases. So when D is multiple of 4, there is a possibility of SPK times SP1. And this is a case when the dimension is 0 mod 4. And this is called the quaternionic Kähler. Actually, this is actually an important class of manifold. but not as a target space of string theory. But for example, in the last quarter, towards the end, we discussed compactification on torus, and we discussed briefly about the Narayan compactification and Narayan moduli space of SOD DD divided by SOD times SOD. The homogeneous space. And this is actually an example of quaternionic Kähler manifold. Unfortunately, the name is a little bit misleading because this manifold is not just not rich flat. So it doesn't satisfy the Einstein equation, but it's even not Kähler. So even though the word Kähler appears in the name, but it's actually not Kähler manifold. So this is actually confusing. There is actually some manifold of this manifold which is Kähler manifold, and it's not really important. But it's a different. It's actually a rather interesting manifold, and it appears in the modular space of certain string theory compactification. There is actually so it's confusingly there is another manifold called with a spin SPK holonomy. Again, D is 4K, and it's called hyper-Kähler. So confusingly, this is actually Kähler. so it's called hyper-Kähler because there are actually more Kähler structure. In general, there are choices of Kähler structure. So for example, the Calabi-Yau twofold, which is called K3, is an example. So complex two-dimensional Calabi-Yau. So we discussed the complex three-dimensional Calabi-Yau because that's the one that we're going to use for compactification of string down to 4 dimensions. But there is a simpler Calabi-Yau manifold, two-dimensional Calabi-Yau manifold. It's called K3. Actually, it's a little bit misleading to say that because there are two types of Calabi-Yau manifold. One is torus. So two-dimensional torus, the 4-dimensional torus is a Calabi-Yau manifold. But that's sort of flat. And so non-trivial example is K3. And so that's an example. So maybe I should just say K3 is an example. Okay, so in this case, actually, there are more supercharges. So in general, you have K plus 1 supersymmetry. Because you have more Kähler structure, so it implies more supersymmetry. So then actually so far we only consider even dimensional manifold. So you can ask, well, is there possibility of compactifying supergravity on odd dimensional manifold and give rise to a supersymmetric solution? And there is one. So there is actually an exceptional holonomy manifold and G2 manifold, and it has a 7-dimensional dimension. So there is only one dimension for which you can have holonomy G2. And this is interesting. You can have n equal 1 supersymmetry. Since we are in odd dimensions, there is no notion of chirality. So you don't classify that with n plus and n minus. You just have n. And it's a minimum number of supersymmetry. It breaks all the supersymmetry. So what it means is that solution to this, is unique. Okay, so this is a very interesting example. And in the case of Calabi-Yau, we have this holomorphic N4, N04. And analog of that is 3-form. And it has the interesting property called associative. I don't have time to explain, but there is associative 3 form, and it's dual. And this is actually a very interesting class of manifold, and it can be useful. For example, if we have time, we will also discuss the M theory, and in particular a version of that for 11-dimensional supergravity. So, in addition to 10-dimensional supergravity theory, which is the low energy limit of type 2 and heterotic string theory, there is actually one more supergravity theory that is interesting, even one higher dimension, 11 dimension. You can have actually supergravity theory more than 11 dimension because you cannot find super multiplet. Maybe I should explain that at some point. But the 11-dimensional supergravity can be regarded as a certain limit of type 2A string theory, and so it's an interesting, and it's the minimum number of supersymmetry. Now, we consider Calabi-Yau threefold because 6 plus 4 is 10, or 10 minus 6 is 4, so we want 4 dimensions. So if you start with 11-dimensional supergravity, you can ask what we can do to get 4 dimension. Well, so one way is to start with G2 manifold. And then consider 4 dimension because 4 plus 7 is also 11. So in fact, therefore, this is actually a very interesting class of manifold because you can use that to compactify 11-dimensional supergravity, giving rise to 4-dimensional manifold. Okay. Unfortunately, the mathematics of G2 manifold is actually still to be explored. So, for example, in the case of Calabi-Yau manifold, there is this beautiful theorem, which says that you can actually understand the entirety of space of solution in terms of complex structure and scalar class, which can be studied in the language of algebraic geometry, so and other powerful mathematical tools. There is no such level of understanding in the space of G2 Holonomy manifold. In fact, there was a Simon's collaboration specifically in trying to address this question, and they made some progress, but I think there are many more things that need to be done. So it's actually interesting. It's a minimum number of supersymmetry. And so that, I think this is an interesting thing to study. And finally, in the Berger's classification, there is a spin 7 manifold, and you have this is also minimum. And analog of that is KD44. So this completes the Berger's classification. And it's amazing that you actually can know all possible holonomy group that the manifold can realize and classify them. And many of them are closely tied to the existence of supersymmetry. So very interesting. In the next lecture, I'll tell you a little bit more about concrete example of Calabi-Yau manifold, and then start using that to understand the compactification of 10-dimensional space to 4 dimensions.